Today's class, we're continuing our work on partial differential equations that we've been working on for a few classes now. So back last week, we looked at numerical solution of Laplace's equation in electrostatics. We looked at numerical solution of heat diffusion equation in thermodynamics. In today's class, I wanted to look at numerical solution of wave equation, and we'll look at it in the context of mechanics, mechanical waves. So it's sort of been a tour through different differential equations. Although they've been different differential equations from different fields, the numerical solutions and the analytical solutions have been rather similar. The methods have been rather similar, and we're just sort of growing or gaining some experience in these numerical and analytical solutions. Okay, to make things concrete, I was going to talk about the wave equation for a string stretched between two fixed points. So it's a string under some tension, and we're going to imagine that we pluck that string under that tension and release that string under that tension, and we'll see a wave propagate along the length of the string, up and down the string. So it's like, you know, you plug a string on a guitar or a violin or whatever. Not that I would ever do that, but if you did, then you would have these string waves that travel up and down those strings. In this little sketch here, I've tried to depict the situation and kind of introduce the language that we'll use for the situation. So just to walk through this cartoon or picture, in blue here is the string. The dashed line would be its equilibrium position, and in blue it's been displaced from the dashed line. In solving this problem, we're going to imagine a small element of that string. So I've sort of pictured that in gray here. Its coordinate, I just called that x, so that's how far from the left-hand end of the string is, and its length is delta x, and its displacement is this y. And that displacement is going to be a function of time, and it's going to be a function of your space coordinates. And it's that displacement will exhibit a wave. And so we're going to develop a wave equation for that wave on the string. There's a couple of parameters in this problem. I should mention those. So L here, that's the length of the string. And rho here is a useful parameter, just the linear mass density of the string. So the number of kilograms per meter of the string. And then, of course, there's the tension in the string. And that's T. And so we're just going to apply Newton's second law. We'll apply it just to this little element of the string. And out of Newton's second law, for that element of the string, we'll see emerge the wave equation for the elements that make up the string. And so that's all I've done on this slide, basically, is start with, at the top of these equations and text, Newton's second law, thinking about that element on the string. And by the bottom of the slide, I've worked to the wave equation for that or in any other element on the string. So here's Newton's second law, F equals ma. Now, specifically, I'm going to be thinking about the motion of that element perpendicular to the equilibrium position of the string. So in this sketch, there's sort of vertical motion of that little mass element of the string. And so that direction I've called the y direction, and we're going to get a wave equation that is a function of one. So here's the sum of the forces in the y direction on the element. And this is mass times acceleration, written in this language, right, of the linear mass density, kilograms per meter, times the length of this little section of the string, delta x. So this is a mass. And then here's the acceleration in the vertical, in the y direction. So now all I've done is plugged in the forces, or the components of the forces that are acting in the vertical direction, that will cause an acceleration in the vertical direction. So this element is experiencing two tension forces on the left-hand and right-hand sides. They're directed along the length of the string. And if the string is not along the equilibrium or that dashed line here, then there'll be a force, a component of the force that's in the vertical direction. There won't just be a tension force in the horizontal direction. And that's what I try to show with these two little arrows here. So we've got tension acting along the length of the string, and you can see there's a small component of tension in the vertical direction. And you can also see, because I tried to draw it, right, that the components in the vertical direction are not equal and opposite. So that there will be a net tension force in the vertical direction. There'll be a net acceleration in the vertical direction. And so I just fill that in down here in the second line. So these are the two components of tension in the vertical direction on the left-hand and right-hand ends of the string. One's positive and one's negative because they're obviously one's slightly upwards, one's slightly downwards. So I rewrote, to get a wave equation, I rewrote the signs of the two angles here using the small angle approximation, because we just displaced the string slightly from the horizontal. So I replaced the signs of these angles in terms of the slopes of the string or the tension force on either side. And that gives this little expression here. So instead of two signs, I've got two slopes on the left-hand and right-hand ends of that little line element. And then I can combine these first-order differentials with this delta x here to make this second-order differential. And this is my wave equation. So in just these few lines, we popped out a wave equation. And the characteristics of the wave equation is we got these second-order differential with respect to the position coordinate is in proportion to the second-order differential with respect to the time coordinate. And the coefficient of proportionality is actually related to the speed of the wave along the length of the string. And you can see it has those units. So downstairs here, where I've rearranged things, we got a second-order differential with respect to time. We got a second-order differential with respect to space here. So for the units to be same on left and right-hand side, the this coefficient of proportionality must have units of meters squared per second squared, and it is the square of the velocity. And so this tells us that the velocity is the square root of the tension divided by the linear mass density. And if you think about that physically, that kind of makes some sense. If you've got a greater tension, that little line element is under greater force, then there'd be greater accelerations. You'll get a greater speed for the wave. If you've got a greater mass or linear mass density, then you've got greater inertia, and that will cause a lesser speed of the wave. So that's where the wave equation comes from on the string. That wave equation has characteristic solutions. I just want to walk through a couple of versions of the analytic solutions for the wave equation, and then we'll move on to the numerical solution of the wave equation. We'll sort of see the pros and the cons of the analytical and the numerical solutions as we kind of go. So on this slide here, I'm picturing the general form of the solution to that wave equation. So the general solution to that wave equation is some sort of propagating disturbance on the string. So if you pluck the string and release the string, that disturbance of the string will propagate along the length of the string, propagate up and down the length of the string if it's reflected at the ends of the string. And so that's what I'm trying to picture here. So mathematically, what that means is that solution of the wave equation, which we wrote as a function of space and time, so of x and t, is actually a combined function of those space and time coordinates. So it's a combined function that looks like this. So x plus vt or x minus vt. V is the velocity of the wave. And so it's a solution of that form that has this property that it looks like a propagating disturbance along the length of the string. And so I try to show that here in these little 3 cartoons, right? So horizontally, I'm plotting the position on the string. And vertically, I'm plotting the disturbance, the wave on the string. And I'm plotting that disturbance at 3 different times. So T1, T2, T3. So T1's the earliest time, T3 is the latest time, T2 is some intermediate time. And so we see this wave in magenta. Imagine to pluck the string like this cleverly. We see it propagating, walking along the length of the string at some velocity. And what this form of the solution to the wave equation dictates is that this shape, this profile here, this disturbance here, just propagates along the length of the string with time. And so that's what we mean by a wave equation. We got this propagating disturbance here. So if we wait some time, so this is at T1, if we wait some time to T2, then this is what that profile looks like. It's just displaced along the length of the string. If we wait from time T2 to time T3, then we just see this propagation, this disturbance at some later time. And so that's really what we mean by a wave equation. It's not some completely independent function of space and time. It's this combined function of the space and time coordinates. You can prove that to yourself pretty straightforwardly. So if we take this idea that the solution is this combined function of space and time, and I write it as this new quantity omega. So this is this combined function of space and time. And I'm going to go through this slide quickly. Just carry out the differentials with respect to the space coordinate and with respect to the time coordinate. Carry out the differentials, the second order differentials with respect to the space coordinate and the time coordinate in this language of this new variable omega. What I'm showing here is I could replace the second order differential with respect to the space coordinate, z or x. I don't know why I changed it to z here. I could replace it with this second order differential with respect to what omega, and I could replace the second order differential with respect to time with v squared times the second order differential with respect to omega. So I'm just changing the language to kind of acknowledge that we're thinking of not separate functions of space and time, but this combined function of space and time. I represented that combined function of space and time as omega equals x minus vt. I've then rewritten the second order differentials with respect to the space coordinate, with respect to this time coordinate, in terms of that single variable omega. I can then replace the second order differentials with respect to space and with respect to time with that differential with respect to omega. So if I plug this equation in to the wave equation and plug this equation into the wave equation, meaning I'm going to replace the second order differentials with the space and second order differential with respect to time with differentials with respect to omega, I get this little equation here, which is manifestly equal to 0, right? So this is just a proof that that the solutions to the wave equation do indeed have this form, this combined function of space and time. So that's one way of looking at the solutions. Another way of looking at the solutions to the wave equation is through separation of variables, and we talked about this last week. So I could take that wave equation and I could, which is again a second order partial differential equation, I can again make this hypothesis that the solution to that equation is can be written as the product of some function of x and some function of time. So I just called those uppercase x and uppercase t. If I insert that hypothesis into the wave equation here, and if I'm differentiating with respect to x, I can pull out the time function. If I'm differentiating with respect to time, I can pull out the spatial function. I get this little expression here, which I can separate out into two parts. So I can move all the space dependencies over to one side, all the time dependencies over to the other side. That's going to turn my partial differentials on the left and right into ordinary differentials, because those sides are only function of either space or of time. And most importantly, it allows me to separate those two parts. Because one's only a function of time, one's only a function of space, they must be equal to one another for any value, any space coordinate, any time coordinate. They must be equal to some constant that we would call a separation constant. And I just define that separation constant here and I pull them apart. So this is separation of variables for the wave equation. Once I've separated the variables for the wave equation, I can recognize the solutions to those separated ordinary differential equations. They're, again, very familiar ones because they're just saying that the second order differential of this function of space, or the second order differential of the function of time, is in proportion to the negative of the original function of space or time. That's what these equations are telling us. We know these have familiar solutions. You could write them as sums of sine waves and cosine waves, or sums of exponentials with imaginary exponents. They contain either the wave number would be a variable, is the separation constant to be determined by your particular problem, or you could write it in terms of a angular frequency, which would again be a variable that would be determined by your particular problem. And they include a bunch of other constants, A's, the B's, the C's, and D's, that are, again, all determined by initial conditions or boundary conditions. I can finally write the completely general solution by writing the product of these functions, the dependence of x, the dependence on time. And here's that product. And you see when you take this product, that combined function of space and time, so x minus vt, x plus vt, that emerges from this in this general solution. So that kind of supports that notion of a combined, the solution being a combined function of the space and time coordinates. Well, that's the sort of analytic solution of the wave equation, both this sort of general form that it depends on combined x minus vt or x plus vt, or a general solution that is some sort of general sum of sines and cosines, or exponentials with positive and negative imaginary arguments to them, and this whole family of functions with different values of the a's, b's, c's, and d's, and so on. For simple cases where you just have a sinusoidal wave on the string, then those are readily sort of solvable analytically. The sort of classic case is a standing wave on a string. So a standing wave on the string, say with nodes at the two ends of the string, that's a particular solution that is embedded in this general solution, and that's one that we can find analytically by applying the boundary conditions. But in general, it's again very hard to find solutions to this wave equation for sort of plucking the string, or in some way displacing the string and seeing how that string wave travels along the length of the string. And that's where a numerical solution is going to be very useful. That's where a numerical solution is going to be very handy. So that's kind of sort of the general background on the wave equation that we're about to solve. Any questions on that?